4.1 is inverse functions. We're going to start off by first talking about one-to-one functions. And the definition of this says that a function f is one-to-one if for elements a and b in the domain of f, a not equal to b implies that f of a is not equal to f of b. That is, different values of the domain correspond to different values of the range. If that does not make any sense to you, it's okay. You can think of a one-to-one function with this very simple definition of function where y has exactly one x. A function where every y has exactly one x. So it first has to be a function, and then every y has to have exactly one x. If you remember, a function is where every x has exactly one y. So let's look and see how we can apply this. The first thing that you'll see is using a horizontal line test. You can use this as a graphical way to show if something is one-to-one. It says a function is one-to-one if every horizontal line intersects the graph of a function at most once. Now you had a vertical line test before. Vertical line test, let's say if it was something like this, then going through a circle, it hits more than one place as it goes through. And so you can make up points for this. Let's say that this was the point 2, 3, and since it's a vertical line, this x value is going to be the same, and maybe it's a 2, -4 for that point. So this violates the definition of a function because you have one value of x that has two different values for y. So it's not the case that every x has exactly one y. Therefore, this would not be a function. Does not pass the vertical line test. Horizontal line test works the same way. Now, if I would draw a horizontal line anywhere through this graph, it would only touch once. So this is one-to-one. You can write just 1-1 as shorthand. And this horizontal line, if I can get it horizontal, it's hitting more than one time as you draw a horizontal line through. So this is not one-to-one. This one, it's only ever going to hit one time. So this is one-to-one. And this one, although it passes a horizontal line test, it's not one-to-one because it doesn't pass the vertical line test. Remember that one-to-one functions have to be functions first of all. So we're going to say that this is not a function. And that's all we really have to say. We could also say that it's not a one-to-one function, but if it's not a function, it's assumed it's not a one-to-one function. It's kind of like saying I cannot be your favorite aunt because I'm not even your aunt. So we'll look at some tests here. These are more algebraic along with the horizontal line test to see if something's one-to-one or not. The test really is showing that f of a equals f of b implies that a equals b. That means that f is one-to-one. In a one-to-one function, every y value corresponds to no more than one x value. To show that a function is not one-to-one, so in other words, right here, for number 2, the test is to show that something is not one-to-one. You need to find at least two x values that produce the same y value. You're finding a counter example. We could say we have the horizontal line test through -1. That means that we have a -1 for our y in both of those places, and this is giving us maybe a 1.8 and a -1.8 for your x's. So definitely does not follow the definition to be a one-to-one function. So you can only use that proof if it's not a one-to-one function. If you suspect that, then you find that one counterexample is all you have to find. You can sketch the graph and use a horizontal line test. And if the function either increases or decreases on its entire domain, then it is one-to-one. And a sketch is helpful here too. An example of that would be something like the cube root graph, or if you had a cubic graph, it's increasing on its entire domain. There's no way that it could not be a one-to-one function. So let's test to see if these are one-to-one functions. And see, we've got a line. We're thinking about what this is. It's a line and goes through the y-intercept 0, -1 with a slope of -3, down 3, right 1, down 3, right 1. This is decreasing on its entire domain. So because of number 4 up here, this we know is one-to-one. Okay. And then this one, square root of x squared minus 9. Let's say that we do the number 1 test here. Let's see if I have f of a is the square root of a squared minus 9, and that's equal to f of b Okay, we want to see, is that true? If we can simplify this and get down to a equaling b, well, this would mean a squared minus 9 equals b squared minus 9. Add 9 to both sides, you get a squared is equal to b squared, and square root of both sides, we get a equals plus or minus b. So a does not equal b, it equals plus or minus b. Therefore, this is not one-to-one. Another thing you could do with this one is sketch it. Just show the graph on your calculator and you can see quickly it's not one-to-one. It's not going to pass the horizontal line test. This is a graph that is decreasing on its domain and always decreasing on its entire domain, so it is one-to-one. Again, you can put that in your graphing calculator and see. This is a parabola, and parabolas, this is a parabola that's opening down. Parabolas are not going to be one-to-one. This one, cube root, that is similar to this family of graphs right here, so this is one-to-one. All right, inverse functions. Now that we have covered one-to-one functions, we are moving on to inverse functions. Now let's look at how functions work. This is the function f. It takes something from the first set called the domain and sends it to an element in the second set called the range. And the inverse function, this is the notation used for inverse function, and it's pronounced f inverse. It's not, as this caution says, it's not a negative exponent. It is a recycling of some notation, and once we're in functions, we know that that -1 in the superscript position means a that we're talking about a inverse function, not an exponent. But the inverse function takes things from this second set and goes this direction with it, sends it to an element in the first set. So it undoes what the f function did. In other words, this is the domain for f and this is the range for f. However, this is the domain for f inverse and this is the range for f inverse. And if you look at the down here underneath the schematic diagram, we've got f of a equals b, And F inverse of B equals A. It switches the input and output. In other words, we would get a point AB with this, but the inverse function switches the x's and y's. Okay? So if we wanted to find the inverse with a function that's defined as a roster set of points, then we could do this. 1, 2, 7, 5, 12, -3. We're just switching the x and y on this. That's all you have to do. Okay. Literally switch places for the x and the y. All right, inverse function is shown here where f composed of g of x equals x and g composed of f of x equals x. If that is true, then f and g are inverses of each other. This is actually how you prove that two functions are inverses of each other. So if you are asked to prove or show or verify that two functions are inverses, you have to compose them of each other. You have to do both of those both ways and show that they are inverses. So we'll take this first one here and show, well, here they want us to determine whether they are inverses or not. So we're going to take f composed of g of x, and that means f of g of x, which means f of 1/3 x minus 3, which is 3 times the new input of 1/3 x minus 3 plus 9. That is x minus 9 plus 9, which is x. So far, so good. And then we're going to take g composed of f of x and do the same operation here. We're putting f of x as the input of the g function, and the g function says 1/3 of 3x plus 9 minus 3. So I have x plus 3 minus 3, which is x. Therefore, f and g are inverses. All right, example 2. Let's try f of g of x, and I get a f of -1/4 x minus 2. This is -4 times my new input of -1/4 x minus 2 plus 2. So this is x plus 8 plus 2, which is x plus 10, not just the x that came out up here. So, and it's not going to be inverses here. We have f and g are not inverses. Okay. All right, finding the equation of an inverse. The big thing here is that you're interchanging x and y. Remember when we were doing the previous examples, you're just switching the x's and y's. Once you do that, then you have to resolve for y and then make sure that you use the proper notation when you're finished. So let's go ahead and try this with a simple example first, and we'll move up in our difficulty level. So you can just dispense with the function notation, just use a y instead. And then now we want to switch or interchange our x and y. Now we're going to solve for y. So x minus 7 is -2y. Divide by -2, and I get y equals an x minus 7 over 2. And then I'm going to have y becomes now, instead of saying y, we'll say f inverse of x equals my x minus 7 over 2. Okay. There's your inverse. Let's see if we can try another. Get rid of the inverse, or sorry, the function notation, and switch your x and y. So this is x equals 2y cubed minus 5, and x plus 5 equals 2y cubed. We're going to divide by 2. So y cubed is x plus 5 divided by 2. Takes a cube root to get the y completely by itself. And don't worry about rationalizing a denominator. We're going to replace f with the y with the f inverse so that we've clearly labeled what the inverse function is. All right, here's another a little more challenging problem. It just takes a little practice. If you find this difficult, then just find a few more out of the book to practice. We're going to switch the x's and y. So x is y over y plus 2. For us to get rid of our fraction, we're going to multiply by y plus 2. So I have xy plus 2x equals y. And then for me to solve for y, I have to get my y's on the same side. So I'm going to say y minus xy equals 2x. Then I'm going to factor out the y so that I can completely isolate it by dividing the 1 minus x. That gives me a y equals 2x over 1 minus x, and I finish by nicely labeling my function as the inverse function of f. Alright, for example 4 here, it looks a little more complicated than the first 3 examples that we did. We have a function of x squared minus 1, and then we have this little addendum here that says x greater than equal to 0. Now the reason for that is that if you look at this function, it is the parabola function shifted down just 1 unit. That's not a one-to-one function. So what they've done is said they only want the x's that are greater than or equal to 0. So they get rid of the left half of that graph, forcing it to be a one-to-one function that way. So what we do is the same procedure as we had before. Just make sure and follow along with your condition. That condition that x must be greater than or equal to 0. We're going to switch our x's and y's, and do it in the condition as well. Change that x to a y. And now I need to solve for y, so I'm going to add 1. I'm going to take the square root. So y is going to be plus or minus the square root of x plus 1. But I know that y is greater than or equal to 0. Okay? If y is greater than or equal to 0, it means that it cannot be negative. So we're going to get rid of this negative because of this condition saying that it must be positive. And so now I finish with my function notation with inverse function of f is equal to the positive square root of x plus 1. You don't have to put this condition there because that function is already the positive, y being the positive square root of x plus 1. All right, we're going to look at making a graph. They did not give us the equation for this function, but we can use the information that's given to be able to sketch the graph of its inverse first off, you see that it is 1 to 1, so it does have an inverse. This point of -2 1/4 for the F inverse graph becomes the point 1/4 -2. So 1/4 -2, 0 1 becomes the point 1 0. So 1 0. 1 2 becomes the point 2 1. And 2 4 becomes the point 4 2. Okay, so there you are. Oop. And if you miss it, you can always go back and try drawing it again a little better. There you go. And it's interesting to note whenever you graph these functions and their inverses, you'll see a pattern that they are symmetric to this line here. If you would fold your paper along this line of y equals x, those graphs would meet up on each other. And kind of a neat thing to think about, because that's the line y equals x. What is it that you do to graph an inverse? You make your y equal x, and you make your x equal y, and there you go. So how fitting is it for it to be actually symmetric to that line of y equals x? So here's some important facts about inverses. If f of x is 1 to 1, then we know that the inverse exists. Domain of f is the range of f inverse, and the range of f is the domain of f inverse. If the point AB lies on the graph of f, then the point BA lies on the graph of f inverse. And the graphs of f and f inverse are reflections of each other across the line y equals x, as we just saw. To find the equation for f inverse, replace f of x with y, interchange x and y, and solve for y, and then that's going to give you f inverse of x, which of course you're going to use the correct notation for. And that's all for this lesson. Go ahead and try that homework. Let me know if you have questions.